Our drought here in Utah has seen the Great Salt Lake recede to unprecedented lows, but we're not the only part of the country that's been short on rain. The Mississippi River is also historically dry right now as
the Mississippi River is vanishing.
The climate crisis is also top of mind for many voters. The Mississippi River is at historically low levels.
Not slowly, not naturally, but bleeding into the earth beneath our feet. Barges sit stranded on exposed mud, bridges are cracking, and levees built for centuries are failing from within. A river that has carved the heart of America for 20,000 years, that carries half the continent's water and over $500 billion in cargo each year, is draining into underground chambers that appeared overnight. Scientists are baffled, engineers are alarmed, and the question that haunts everyone is simple, terrifying. Where is the water going? And can we stop it before the Mississippi becomes a ghost river, a dry scar across the country? Beneath the Mississippi. In the summer of 2021, small sinkholes began appearing along the banks of the Mississippi River in Missouri.
To Oktibbeha County, where a new sinkhole at the county lake.
The minor anomalies at first, unusual turbidity readings in Louisiana, water temperatures that didn't match seasonal patterns. Nobody connected the dots. By 2022, the warning signs became impossible to ignore. In September, sections of the river at Memphis measured just 2.5 feet deep, waters that should have been over 20 feet. Barges sat stranded on mud, grain exports stalled, and the river that once carried the heartbeat of America slowed to a crawl. Satellite imagery from NASA's Landsat 9 and the European Space Agency's Sentinel satellites revealed a shocking truth. This wasn't ordinary drought. The riverbed itself was collapsing. Sections dropped 3 to 5 feet over 18 months, far faster than natural erosion could explain.
Mississippi River is nearing historic lows. The river is just below 5 feet.
Hydrological engineers, including Dr. Sarah Chen with the Army Corps of Engineers, were among the first to raise alarms. Sonar surveys revealed voids beneath the riverbed, cavities the size of cars and houses, hidden beneath centuries of sediment. The Mississippi, a river that drains 41% of the continental United States, was literally bleeding into the earth. The economic impact was immediate. More than 2,000 barges were stranded. Grain exports from the American Midwest, the breadbasket that feeds much of the world, ground to a halt. The Port of New Orleans, handling 60% of U.S. grain exports, saw throughput drop by 73%. Supply chains for petroleum, chemicals, steel, and coal fractured overnight. Economists warned of cascade failure and systemic collapse. Historical data made the crisis even more alarming. River gauge records dating back to 1872 show natural droughts and floods, but never anything like this. Sections of bedrock, ancient limestone, and sandstone were exposed for the first time in recorded history. Fossilized mastodon bones, Pleistocene river channels, even traces of pre-Columbian waterways emerged, as if the river were rewinding through geological time. But the uncovered history mingled with modern hazards. Decades of industrial waste, rusted drums, and abandoned machinery lay exposed on the riverbed. In some areas, geometric drill patterns suggested human excavation. Meanwhile, Memphis detected unusual mineral fluctuations in its drinking water.
Our drinking water comes from the Memphis Sand Aquifer.
Fox 13 health reporter Mandy Rock exposes the danger to our drinking water.
By early 2023, salt water from the Gulf of Mexico had crept 45 miles upstream, contaminating freshwater supplies for hundreds of thousands. Emergency measures, including an underwater sill to block the salt water, provided only temporary relief. And the Mississippi's weakening flow also destabilized navigation. Towboat captains reported unusual vibrations beneath their vessels. In February 2023, a tow struck unexpected solid rock near Greenville, Mississippi, rupturing a barge carrying anhydrous ammonia. Toxic chemicals were released into the river, forcing evacuations and killing aquatic life for miles. Surveys using multi-beam sonar, seismic imaging, and drone-deployed sensors confirmed the unthinkable. The river wasn't just shallow. It was actively draining into an underground network of cavities. A subterranean plumbing system, likely accelerated by decades of industrial activity, mining, and chemical contamination, was siphoning the river away. This is more than a hydrological crisis. It's a warning about the fragility of the systems we rely on. The civilization assumes rivers are eternal, bedrock unchanging. The Mississippi shows us how wrong that assumption can be. The river's collapse threatens commerce, agriculture, water security, and ecosystems on a massive scale. The water is still flowing, but for how long? And as the river drains into the darkness beneath our feet, one question looms. Are we witnessing the first domino of a chain reaction that could reshape the American landscape forever? The hidden drainage nightmare. When comprehensive sonar mapping began in March 2023,
but with new technology, projects are underway through the water, using sonar to scan the seabed.
scientists expected to find minor riverbed erosion. What they discovered shocked them. The Mississippi's bedrock had become a labyrinth of cavities. Swiss cheese, as geophysicists described it. Multi-beam sonar revealed craters, sinkholes, and voids hundreds of feet across, riddling areas beneath the river that were supposed to be solid. The largest measured 200 feet in diameter and 60 feet deep, directly under the navigation channel near Baton Rouge. Smaller cavities, from 10 to 50 feet, numbered in the hundreds. Dr. Marcus Webb, a geophysicist at Louisiana State University, led one of the survey teams. I've mapped ocean trenches, subglacial lakes, underwater volcanoes, he said. But this? Patterns of voids aligned with fault lines and industrial discharge points. Something unnatural is happening. The geology of the Mississippi Basin, limestone, sandstone, and shale, is naturally prone to karst formation, where slightly acidic water dissolves rock over thousands of years. But the cavities forming under the Mississippi appeared within decades. A ground-penetrating radar confirmed extensive fracture networks that sometimes extended over 150 feet, connecting river channels to deeper aquifers, including the Mississippi River Valley Alluvial Aquifer, which provides drinking water to millions. Hydrological models estimate the river is losing 15 to 20% of its flow to subsurface drainage, millions of gallons vanishing daily. While some water enters aquifers, measurements suggest other flows are being siphoned into deeper unexplored channels, possibly following fault lines or porous rock formations miles underground. The river was developing a complex underground plumbing system, accelerating as more voids appeared. Core samples revealed the mechanism. Once solid limestone and sandstone had become porous, friable, and crumbling. Water had enlarged microscopic pores, connecting previously isolated voids into continuous channels. Surveys repeated in August 2023 showed exponential growth. Cavities expanding, new voids appearing, creating a feedback loop of structural collapse. Engineers warned of a cascading failure, where each new fracture undermines the surrounding rock, creating new pathways for water to escape. Remote sensing confirmed the danger. Satellite synthetic aperture radar detected widespread subsidence along the river, millimeters to centimeters in critical zones. Subsidence alters flow, weakens levees, and can trigger sudden collapses. In June 2023 near Vicksburg, a 50-foot wide section of riverbank collapsed into the Mississippi.
The Mississippi has reached its crest here at Vicksburg,
temporarily blocking part of the channel and creating a navigation hazard. Though no one was hurt, the collapse highlighted the risk. Entire riverbanks, and industrial facilities, and even city infrastructure could be perched atop hidden voids. The causes are becoming clear. Decades of industrial activity, chemical runoff from agriculture, and wastewater discharge have altered the river's chemistry, accelerating the dissolution of limestone and sandstone. Acidic runoff, fertilizers, and salts have increased water corrosivity, turning processes that normally take millennia into phenomena unfolding in mere decades. The Mississippi River, artery of commerce, history, and life, is being drained from below while simultaneously being poisoned from above. Millions depend on it for water, transportation, and food production. Yet beneath its surface, cavities grow faster than anyone anticipated, threatening navigation, infrastructure, and aquifers. The crisis is ongoing. Monitoring networks, tilt meters, geophones, continuous GPS track movement in real time, but they are reactive, not preventative. The river, once assumed stable and eternal, has revealed itself to be fragile, vulnerable, and transforming before our eyes. The real question now is not whether we can fix it, but whether we understand the scale of what's happening before catastrophe strikes. River that eats the earth. The Mississippi River has never been pristine. Since European settlers established industries along its banks, the river became a dumping ground for industrial and agricultural waste. But in 2023, scientists discovered a far more alarming reality. Decades of pollution hadn't just contaminated water, they had fundamentally altered the river's chemistry, actively dissolving the limestone and sandstone bedrock beneath it. The investigation began with a massive water chemistry survey from Minnesota to Louisiana. Samples revealed familiar pollutants, nitrogen and phosphorus from agriculture, heavy metals, petroleum residues, and industrial organic compounds. But the alarming discovery was the acidity. Sections of the river registered a pH as low as 5.8.
The next test is to measure the pH of the Hawkesbury River water. Your result will be somewhere between 0 and 14, which is the pH scale.
Approaching the acidity of tomato juice. While harmless to humans for brief exposure, such acidity is catastrophic to limestone, which dissolves rapidly under slightly acidic conditions. Chemical analysis revealed the culprits: anthropogenic acids. Sulfuric acid from coal-fired power plants and industrial facilities, nitric acid from fertilizer runoff, and organic acids from chemical manufacturing were present at levels that had never been studied for geological impact. Dr. Jennifer Torres of the EPA likened the process to dripping lemon juice on chalk for decades. Slow, almost invisible, but ultimately destructive. Agricultural runoff intensified the problem. Nitrogen-based fertilizers break down into nitric acid, while phosphate fertilizers alter water chemistry to accelerate rock dissolution. Industrial chelating agents, used in textile, paper, and chemical industries, bind calcium ions and directly strip them from limestone, dissolving bedrock faster than acids alone. Historical analysis revealed a pattern. The worst damage occurred downstream from major chemical plants, refineries, and industrial complexes, particularly in Louisiana's Cancer Alley, home to over 150 industrial facilities. Laboratory tests confirmed the mechanism. Rock cores submerged in actual Mississippi River, water dissolved measurably within weeks, while controls in clean water remained intact. Synergistic chemical interactions, where compounds amplified each other's effects, created a chemical reactor out of the river itself. Thermal pollution added another layer. Industrial facilities discharge heated water, raising local river temperatures. Higher temperatures accelerate chemical reactions, including limestone dissolution. Climate change compounded the effect by increasing ambient temperatures and altering river flows, concentrating pollutants during low water periods. Infrastructure amplified the crisis. Bridge foundations, levees, pipelines, and port facilities penetrate sediment layers that normally protect bedrock. Abandoned pipelines, corroded drilling casings, and utility crossings created pathways for chemical-laden water to infiltrate deeper rock layers, spreading dissolution underground. The Interstate 40 bridge in Memphis, for example, sits atop bedrock showing cavities that threaten the pier's structural stability. Even cities felt the effects. Memphis's bluffs exhibited early signs of subsidence, while New Orleans, already below sea level, faced heightened flood risk as levees weakened.
For New Orleans, water rushed in as dozens of levees failed, flooding 80% of the city and leaving over 1,300 dead.
Farmers reported sinkholes swallowing equipment, and water treatment plants struggled with unusual mineral content and fluctuating pH, complicating potable water production. The Port of New Orleans experienced a partial dock collapse in September 2023 due to a void beneath its foundation, disrupting $100 billion in annual trade. Yet the roots of the problem stretch back over a century, but accelerated after World War II, when industrial output and chemical production surged. Regulatory protections, including the Clean Water Act of the 1970s, mitigated some pollution, but were too late and limited in scope. Many chemicals now known to attack bedrock, chelating agents, industrial organics, thermal pollutants, were unregulated then and remain partially controlled today. Even natural processes contributed. Nutrient overloads fuel algae blooms, which decompose and release carbon dioxide, forming carbonic acid and further increasing water acidity. Certain acid-producing bacteria were found colonizing bedrock surfaces, generating localized chemical attacks directly on rock formations. The pharmaceutical residues from municipal wastewater added low-level but persistent chemical stress. The cumulative impact is profound. The Mississippi River, a lifeline for transportation, agriculture, and industry.
Historic low levels on the Mississippi River coming at the absolute worst time for farmers, the heart of harvest,
has become a geological weapon against itself. Each gallon of water carries a chemical payload capable of dissolving the rock it flows over, threatening bridges, levees, pipelines, ports, and cities. Stopping or even slowing the process will require decades of investment in pollution control, sediment management, and infrastructure reinforcement. Even if industrial discharge ceased tomorrow, the chemicals already in the system would continue their destructive work for years. The Mississippi River is no longer just a river. It is a living chemical experiment, reshaping the land beneath it, attesting the resilience of every structure along its banks. Humanity now faces the challenge of managing a river that is actively dissolving the foundation of civilization itself. Foundations under fire. On the morning of July 15, 2023, engineers inspecting the Interstate 40 bridge over the Mississippi River in Memphis made a startling discovery. Using ground-penetrating radar and ultrasonic testing, they detected massive voids beneath the bridge's pier foundations, cavities in the bedrock so large that they threatened the stability of a structure designed to carry 60,000 vehicles daily. The I-40 bridge, also known as the Hernando de Soto Bridge, is a critical artery in the interstate system. A collapse would not only endanger lives, but also disrupt commerce across the heartland. Built in 1973, and the bridge's foundations were drilled deep into bedrock, following engineering assumptions that rock would remain stable indefinitely. Nobody anticipated that the bedrock itself could dissolve over time. Emergency inspections revealed stress fractures and uneven settling in the piers, early signs that the bridge could become structurally compromised within 5 to 10 years without intervention. The I-40 bridge was far from unique. A Federal Highway Administration survey of Mississippi River crossings revealed similar warning signs: subsiding piers, cracks, and voids under multiple bridges, including the new Chain of Rocks Bridge, the Eads Bridge in St. Louis, the Greenville Bridge in Mississippi, and the Vicksburg Bridge. Engineers coined the term systematic infrastructure vulnerability to describe the scale of the problem. Reinforcing these structures would require billions in investments, underpinning foundations with deep piles, grouting voids, and constant monitoring. Bridges were only the beginning. The Mississippi River levee system, stretching over 3,500 miles, protects millions of people and trillions in property. Many levees sit atop or near bedrock compromised by dissolution. Some sections already show differential settlement, creating weak points that could fail under flood conditions. A levee failure on the lower Mississippi could rival the devastation of the Great Flood of 1927.
The Mississippi Flood of 1927 was one of the most catastrophic floods in U.S. history,
which killed hundreds and displaced 700,000 people. Today, modern levee failure could affect millions. Emergency stabilization efforts by the Army Corps of Engineers are ongoing, but resources are insufficient to secure the entire system in time. And the crisis extends underground. Pipelines carrying crude oil, natural gas, and chemicals crisscross the river corridor. Subsurface voids and uneven settling threaten to rupture these conduits, causing environmental disasters and economic disruption. Smart pigs, inspection robots, have already identified cracks and stress points in several pipelines, prompting emergency shutdowns that disrupted fuel supply in multiple states. At the river's mouth, the Port of New Orleans illustrates the human cost of geological instability. In September 2023, a dock partially collapsed when a void beneath it gave way, toppling containers and shutting down operations. Repairs were extensive and costly, and inspections revealed that other port facilities required foundation reinforcement. Water and power infrastructure is also at risk, and treatment plants face chemical and pH fluctuations in river water, while cooling systems for nuclear and fossil fuel plants depend on stable river flows and secure foundations. In 2022 to 2023, low river levels forced some plants to reduce output, and geotechnical instability added structural risk. The Nuclear Regulatory Commission has mandated enhanced monitoring at river-adjacent facilities. Cities themselves are vulnerable. Memphis sits atop a bluff showing early signs of subsidence, while New Orleans, already below sea level, is increasingly exposed to flooding as levees weaken. Property insurers have begun reassessing risk, threatening to make some areas uninsurable, and farmers are losing land to sinkholes and uneven subsidence that disrupt irrigation and drainage. The cascading nature of these threats, bridges, levees, pipelines, ports, power plants, water systems, creates a perfect storm of interdependent risks. A levee breach could flood pipelines. A bridge collapse could delay emergency response. A pipeline rupture could exacerbate environmental damage. Emergency management agencies are developing worst-case scenario plans, but the complexity and scale of the risk challenge even the most prepared systems. Federal disaster declarations are ill-suited for a slow-motion catastrophe. This is not a hurricane or earthquake. It's a chronic emergency.
We have typhoons and recently earthquakes as well, but we are just braving and weathering these storms.
A century-long crisis accelerating as bedrock dissolves and infrastructure settles unevenly. Engineers can design interventions, but success depends on unprecedented coordination, funding, and speed. The Mississippi River crisis is a stark reminder that human infrastructure assumes a stable earth beneath it. But beneath the bridges, levees, pipelines, and ports, the rock is dissolving. The clock is ticking, not in hours or days, but in the slow, relentless erosion of the foundations we've always taken for granted. The canary in the coal mine. If the Mississippi River crisis existed in isolation, it would be catastrophic enough. But research suggests it's not unique. It may be a warning about rivers worldwide where human activity has altered water chemistry enough to trigger geological changes. Scientists began surveying major rivers with similar industrial and geological conditions. The findings were alarming. Europe's Rhine River, flowing through the continent's most industrialized regions, showed early-stage cavity formation in limestone sections. A water chemistry revealed elevated acidity and industrial pollutants similar to those devastating the Mississippi. In China, the Yangtze River, draining massive industrial and agricultural zones, was losing water in its middle and lower reaches. Authorities had previously blamed drought and irrigation, but geological surveys suggested subsurface drainage through compromised bedrock could be a contributing factor. India's Ganges, a sacred river for millions and heavily polluted, flows over limestone and sandstone in its lower reaches. Preliminary studies suggested bedrock dissolution was occurring, though monitoring was limited. Even smaller U.S. rivers like the Ohio and Tennessee displayed early-stage cavities, confirming that human-accelerated rock dissolution is not limited to the Mississippi. But the pattern was clear. Rivers flowing over soluble rock while receiving industrial or agricultural runoff are vulnerable. Natural karst formation typically takes thousands to millions of years. Human activity, however, has accelerated the process, creating geological changes in mere decades. Acidic water, chemical pollutants, and thermal discharges combine to dissolve limestone and sandstone far faster than nature ever intended. Climate change compounds the problem. Altered precipitation patterns concentrate pollutants during droughts and increase erosion during floods. Higher temperatures accelerate chemical reactions, including rock dissolution. Extreme weather events threaten infrastructure already weakened by unstable geology. But yet both climate change and the geological crisis share the same root cause: unsustainable industrial practices. Fossil fuels generate greenhouse gases and pollutants that destroy rivers from below, showing that the two crises are interconnected symptoms of the same industrial age pressures. The impacts extend far beyond geology. The Mississippi River ecosystem, already stressed by pollution, faces additional threats. Fish populations decline as water chemistry shifts, wetlands dry up, and migratory birds along the Mississippi Flyway lose habitat. The Gulf of Mexico dead zone, an oxygen-depleted area caused by nutrient pollution, has grown unpredictable. Changes in sediment and nutrient delivery disrupt fisheries and accelerate coastal wetland loss in Louisiana, reducing natural hurricane protection and affecting carbon storage in soils. The crisis also affects global trade. The Mississippi is a vital artery for grain exports and industrial shipping. Any disruption threatens international food security. Events like the partial dock collapse at the Port of New Orleans in September 2023, caused by subsurface voids, highlight the risks to commerce and infrastructure. Bridges, levees, pipelines, and ports built on compromised geology are at increasing risk. In Memphis, limestone bluffs supporting the city show signs of instability. In New Orleans, subsidence combined with levee vulnerability could magnify flood risk. Water security is a growing concern. Polluted river water infiltrating aquifers could spread contaminants hundreds of miles, crossing state and national boundaries and creating potential public health crises. Economically, decades of industrial activity generated trillions in short-term value, while causing geological damage that could cost even more to repair, if repair is possible at all. This raises profound questions about growth itself. Can prosperity built on the destruction of foundational natural systems truly be called progress? Legal and ethical challenges follow. Environmental laws focus on individual pollutants or violations, but the Mississippi crisis results from centuries of cumulative, often legal actions. Communities have filed class action lawsuits against corporations and government agencies, but resolution may take decades. Technological solutions, stabilizing bedrock, chemical treatments, geoengineering, exist in theory, but scale, cost, and potential unintended consequences are daunting. Some scientists hope the crisis could drive innovation in pollution control, geological management, and sustainable industry. Others caution that knowledge alone doesn't guarantee action, particularly when economic and political interests resist change. The Mississippi River is both a lifeline and a mirror. It reflects the consequences of industrial civilization's short-term thinking. Beneath the water, the ground is dissolving, threatening infrastructure, ecosystems, and economies. The future depends on choices made now. Act decisively, and the river may recover, fail, and generations inherit a dry scar across the continent, a cautionary tale of a civilization that undermined its own foundations. The Mississippi is more than a river. It's a warning etched into the very ground beneath us. What we see on the surface is only a fraction of what's happening below. Cavities swallowing water, bedrock dissolving, systems unraveling. Every drop that vanishes carries a story of centuries of human ambition, and the consequences we never fully understood. So the question isn't just how we save a river. It's what other invisible fractures are forming beneath our feet, waiting for the moment we finally notice. And when they do, will we be ready? Or is the next collapse already quietly underway?